Okay, let's see this example. So here you can see most of these loads will be transferred vertically downwards. So the total length of the beam is 5200 millimeters. So the load over 1000 millimeters will be transferred directly. So the remainder will be 3200 millimeters. So in this case with wide supports, part of the load at the top of the wall can be transferred directly. Only the UDL acting between supports need to be transferred with the strut and tie. So the length is 3.2 meters. So which means the concentrated load C1 will be due to half this length, and the loading intensity is 600 divided by multiplied by 3.2 divided by 2, 960 kilonewtons. And this also gives an indication of the strut angle. So it's something like this. So we can see this one, still considering that this height as 2000 millimeters, and also considering that this strut forces will be transferred to the center of the support, So I have considered that this angle is due to 800 millimeters here plus another 500 millimeters. So the angle will be 2000 divided by 800 plus 500. So angle has been considered as 2000 divided by 800 plus 500. So the angle has been considered as 57 degrees. So based on that, you can work out C1 is known. C1 is 960 kilonewtons. So C3 can be worked out. C3 is C1 divided by sine 57, which is 1144 kilonewtons. And in addition to that, you can work out the force in the tie. Force in the tie is 589 kilonewtons, or it is equal to C1 divided by tan 59, or C3 cos theta. Both gives the same answer, 589 kilonewtons. So the area of reinforcement in the tie is calculated as we have done earlier. Again, you can see you need 2 numbers of 20 millimeter bars and 4 numbers of 16 millimeter bars. And the tie reinforcement has not changed much. It remains pretty much the same. Although early example, the load was 350 kilonewtons per meter. Here the load is 600 kilonewtons per meter. So you can see this is a heavily loaded beam, but having wide supports. So the vertical load is 960. So once you work out these values, you will find that C3 is 1144 and T1 is 589. So you will find that the reinforcement is similar to the earlier one, but now it carries a much higher load, 1432 millimeters squared. So which means, we can consider that the vertical height that we transfer is also 360 millimeters. But here the advantage is we have a wide bearing. Because the bearing is wide, you'll find that the strut angle is also higher. Whereas if you look at the stressors that this can resist, they will remain more or less the same. So these are CCC node 15, CCT node 12.75. And if you look at the width of the strut in our case now, 1000 cos 33, because the angle is 57, plus 360 cos 57, use 1034. So you can clearly see the angle has increased, sorry, the width has increased. And when the width increases, we have a particular advantage because the stress in the strut will be reduced. So stress in the inclined strut due to C3 is 4.42 newtons per meter squared. Is very much lower than 12.75. So we don't have to worry about it. And then there's another issue. That means, you know, here now the loads are coming at an angle. Here the loads are coming vertically. All those loads are meeting at a place like this. So sometimes you might consider that, you know, continuing some of this the support reinforcement within the wall to a height like, you know, 1 meter sometimes. So that will ensure that, you know, whatever the effect of the stress concentration can be sorted out. But if you look at the force carrying capacity of concrete alone for this support, it is fairly higher than, very much higher than this the load, the total load that this column has to resist. So we can't expect any problem. So the main advantage of having a pile with a pile cap supporting the wall is, you know, we get, because the pile cap is wide, we get a fairly wide rigid zone, and that will actually help us to reduce the stress in the strut. Now here you can see the stress in the strut is only 4.42 newtons per millimeter square. So this way we can improve. So in this wall, what you have calculated is only the tie, and you have checked the strut, but still we have to make sure that we have additional reinforcement for resisting the tendency for thermally induced cracking and so on. So shrinkage cracks, thermally induced cracks, so all those should be avoided, and the easiest way to avoid those is to provide the minimum reinforcement that is needed within the deep beam. So the reinforcement needed within the deep beam is something like 150 millimeter squared per meter, but there's a maximum distance of something like 300 millimeters. So if you use 8 millimeter horizontal bars, and then 8 millimeter bar has an area of 50 millimeter squared. So you can see by providing 8 millimeter bars at 300 center to center, we can easily reinforce the rest of the deep beam. And in case that, you know, it's not a deep beam specifically meant for deep beam, it is a wall acting like a deep beam, because this is a concrete wall that is used in the building. But at the ground level, you know, we are trying to support it only at the two ends. So then the beam which has behaved in the normal way will become a region with concentrated loads. So because of that reason, we can go with strut and tie and design the wall as we have done in the example. But when you do that, you have to provide additional reinforcement. The additional reinforcement is, you know, whatever the wall reinforcement, and the wall reinforcement is not a very high amount. the wall reinforcement is the minimum is vertical direction 0.002%, so 0.002 times area of concrete, which gives a very low requirement. And then the horizontal direction, you have to provide either 25% of the vertical reinforcement or a minimum of 0.001 in the horizontal direction, 0.001 of concrete area in the horizontal direction. But again, in the horizontal direction also, there's a maximum spacing of 400 millimeters. So in the vertical direction, there's a maximum spacing of 300 millimeters. Sorry, that's in the case of deep beam. But if it is a wall, again, the maximum distance is 400 millimeters between two adjacent bars in both vertical and horizontal direction. But it cannot exceed 3 times the wall thickness either. So basically, you can see now this is one of the possibilities that you might encounter with pile foundations, where the two piles are supporting a wall. So in that situation, in the upper part of the wall will behave just as a normal wall, whereas at the ground level, the wall will behave in a different way. To analyze that, you will need a strut and tie model, because now the wall is subject to concentrated loads. So all the loads that comes from above should be transferred onto the supports. So because of that reason, you'll get concentration of loads and also changing of load paths. To take account of that effect, you have to provide some additional bottom reinforcement in the wall at ground floor level. And in addition to that, you can provide the normal wall reinforcement as well. And if you think the stresses are high, there's a possibility of continuing part of the column reinforcement and anchoring it within the wall, so that any stress concentration effect also can be very well taken into account by the column reinforcement. So that's the way that we can make use of strut and tie models for the design of walls supported directly by the piles. And there's another application for strut and tie model, and that's in the case of pile caps. That is in the case of pile caps. And we used to call it truss analogy, but basically it's also truss and strut and tie model. Strut and tie model. So any questions on this? Any questions, please? Dean? Dinesh? Yarandana? Ashar? And Anjali? Do you have any questions? Manjula? No. So then shall we move to the next section, and that is on the design of pile caps. So next time I'll show you how to do a complete model of a building, including the pile caps and piles. So today we look at how to design pile caps using the same theory. That is the strut and tie models. So in most of the time, we support the loads by using a pile cap, which will be able to transfer the loads onto the pile. So pile cap should be rigid enough to transfer the column loads. And also, we need to have sufficient space for anchoring the pile reinforcement within the pile cap. And also we are starting the column bars within the pile cap. So there should be sufficient space for anchoring and, accommodating all these reinforcement. So one of the options available is to design the pile cap as a strut and tie model, or we call it truss analogy as well. On the other hand, you can design the pile caps by considering that it behaves as a beam as well. So that's also possible. So this is a truss and tie model, which is very similar to what you have just seen and discussed. And these are the guidelines that are given in the structural engineering manual, so the manual by Institution of Structural Engineers for pile caps. So what's given here is whatever the guidelines they have given, and generally it's recommended to have piles at 3 times the pile diameter. And you'll ask what is the reason. The reason is, when you do a pile with socketing, then, after a while, you will do another pile next to it. But if these two piles are very close, then when you do the socketing, when you are breaking the rock to make the socket, there is a chance that you might damage the pile that you have already completed. So because you are crushing the rock very close to a pile where the pile has already been cast. So that is not a desirable situation. So because of that reason, certain distance is recommended between two adjacent piles. So the recommendation is 3 times the pile diameter. But if you look at ICTAD specification and so on, for end-bearing piles, it allows you to reduce this distance up to 2 times diameters. Whereas, in cohesive soils, so if you are relying a lot on skin friction, you can go up to about 2.5 times diameters. Sorry, 3 times diameters. You have to go up to 3 times diameters if you are relying a lot on cohesion. So in our conditions, we actually rely on both cohesion and or the friction and end bearing. So it may be a good practice to remain close to 3 times diameters if you cannot strictly follow 3 times diameters rule, especially when you go for large diameter piles. So if you have 1 meter pile, the distance between two adjacent piles will be 3 meters, whereas it will increase to 3.6 meters when you go for 1.2 diameter piles. So this 3 times diameter rule is sometimes little difficult to fully comply with, but you can come pretty close to that. And also it says piles should be grouped symmetrically under load, and if you have a symmetrical arrangement carrying only the axial load, then the load on all piles can be taken as equal. Whereas if the pile is subjected to an axial load and a significant moment, then some piles will be loaded more than the others. And if you have single columns or single piles, then the pile should be capable of carrying an eccentricity of 75 millimeters, or the bending moment induced due to a 75 millimeter eccentricity. Or otherwise, you need to have ground beams that can actually resist this additional moment. The reason is, it's very difficult to cast piles at the exact location that you want, always you will get a slight variation in the pile locations. So generally the number of piles are selected. This also from this structural manual. What they say is the number of piles should be selected based on the unfactored load, and then you can use factored load for the design of the pile cap using strut and tie model, or by considering it that it behaves as a beam. And also it's necessary to determine the depth of the pile cap. Generally the depth of the pile cap can be considered as equal to the distance between the center of the load and the furthest point that the pile foundation is acting in case of pile caps having up to 5 piles. But if you have a pile cap which is longer than something like have support around 6 piles or 8 piles, then you have to just check the punching shear and direct shear and see whether the selected depth is adequate. So general rule is, the depth that you select can be half the distance between two adjacent piles, plus some additional allowance to allow for the cover to the reinforcement and all that. So generally what we do is we take half the distance between two adjacent piles and add 300 millimeters to it, and that will give the size of the pile cap. And then you will get the piles arranged like this, and then to determine the when you go with strut and tie model, to determine the force in the tie, there are simplified equations that have already been derived, where T is a function of NL over 2D, but here you can see L is the distance between two adjacent piles is taken as 2 times L. So yeah, when you are using this equation, you have to be a little careful, because here the L means half the distance between two piles, whereas the distance between two piles has been taken as 2 times L. So you have to be a little careful when you are using this particular equation. So once you select the reinforcement in the pile cap by using the value of T that you calculate from these equations, then you have to check it for shear. But in case of a pile cap, if the distance between two piles is 3 times diameters, and then you have a column also supported, then there isn't much space for punching shear failure, because when you are very close to the concentrated loads, you will get the enhancement of the shear capacity. So when you consider the enhancement of the shear capacity, you will find that it's hard for a pile cap to supported by 4 columns located 3 times diameters or less to fail in shear. Whereas if you are having the piles at more than 3 times diameters, then you can see whether the punching shear failure also can happen. So you can see whether the punching shear failure also can happen. And the kind of punching shear failure, the perimeter, punching shear perimeter is given by 2 times diameters, sorry, 2 times depth, 2 times effective depth. So this is the punching shear perimeter. And in addition to that, you have to also check for direct shear. But if the piles are close, something like 3 times diameters or less, then you don't have to really check for punching shear, because there's very little chance of punching shear to happen. But still you have to check for direct shear. You have to still check for direct shear. So those are the basic rules. And then there are a few examples that I have done. And we look at these examples next time, because there are a few things to be discussed. And so we'll discuss this in greater detail next time. So do you have any questions that you like to ask? And also, because this, we have adopted this semester system, you have to do. We are supposed to give you few assignments as well. So I will prepare an assignment on an inverter T-type beam, where you can do a model and get the bending moment diagram and perform the structural design for an inverter T-type beam. And for the batch, I will give different soil properties, so that you will get different answers, and later we will be able to share the details of different cases, so that we can get an idea that what the type of variations that we can get in an inverter T-type foundation. So we'll go for a inverter T-type foundation supporting 4 to 5 floors with bearing capacities varying between 75 to 125 kilonewtons per meter squared. So, and also different grid arrangement, so that the loads transferred will be different, so as the length of the foundation will also be different. So we'll be able to see how the stiffness of the soil will affect the bending moment variation, bending moment diagrams that we get under the inverter T-type foundation. So we'll do an assignment based on your index number, so that we'll be able to generate a reasonable number of different solutions that we'll be able to see, compare and see later. So we'll do an assignment like that, and later we can do another assignment of a building where foundation is also modeled, so that you will have a reasonable idea about different modeling techniques and also the design techniques for foundations. So with that, shall I end the lecture? And if you have any question, you can ask it now.
So,
yeah.
Some code described about anti-bursting reinforcement in the file cap. Like in these codes, how about your opinion of this anti-bursting reinforcement?
No, actually, it comes with the Strut and Tie model, because what happens is, now here you can see we have considered the tie to be prismatic, right? But if you look at the Euro code, I'll show you where to. Now here you can see. Now what happens in a tie is, now we are transferring the load here. We are transferring the load here. But the tie will have a bigger area. And so if this is happening, then the Euro code actually specify you to provide some reinforcement this way, horizontally. And that's the type of reinforcement that we call anti-bursting reinforcement, right? But because the pile cap is fairly large, and also we have this horizontal reinforcement surrounding the pile cap, generally this will not be a major problem. But if you actually look at it, you know, what actually happens is we have a concentrated load, and at the pile also we have a concentrated load. So in between, when you have concrete, there will be a, you know, a bigger area resisting the contributing to the strut, and actually we should be providing some reinforcement horizontally to ensure that this compression strut has sufficient confinement. But what actually happened is, because we are having a pile cap which is fairly large, and also because we are having the reinforcement at the top and bottom and also on the sides, generally, you know, we do not try to provide this. There's another reason, and that is, you know, we get the column reinforcement also continuing to the bottom, and also pile reinforcement also continuing. So there's a certain amount of reinforcement, but theoretically we should be actually providing some ties in the pile cap. Only thing is, you know, in practice, you know, we generally do not go for it. But if a code says, you know, you have to provide anti-bursting reinforcement, it's true because this is the reason for it. Is that clear?
Okay, sir. Yes.
Yeah. So you can see it's actually given in Eurocode. Only thing is, our practice is, you know, we do not worry too much about it because this reinforcement requirement will be fairly small. And because the pile cap is large, generally we do not get this particular problem. But it can actually happen. And this is the explanation, right?
So in the Indian code, they mention about 25% of the main is steel.
Main reinforcement horizontally.
Yes, yes.
Within the
body of pile.
Within the body of the pile, and this is the reason for that. You can see. So here the equation for calculating the tension is also given.
Okay.
And the tension reinforcement should be within this area. And if you want, you can distribute this reinforcement over the full length as well. So that's what given in Eurocode also. Only thing is, you know, you can't find much literature which says, you know, this reinforcement should actually be provided within the pile cap. Because, you know, we are going with the simplified assumption that, you know, we are having a prismatic arrangement. We are having an arrangement like this. No distribution of this force. So actually what happens is, when there's no distribution of this force actually becomes fairly small. And in such a situation, you know, you don't get any bursting. That's true. So whereas, you know, if this force is concentrated, then there could be a possibility for bursting. So this Indian code maybe actually they would have had some experience and they would have gone for this reinforcement. That is the explanation.
Okay, so thank you.
Yeah. Any other question? So in that case, shall we end the lecture, and I'll upload the recordings, and within 1 or 2 days I will upload the assignment so that you can attend to it, and we'll do it with index number base, so that, you know, we can generate a large number of solutions, so that we can see what happens under different soil parameters and also different spans and so on. Okay, so in that case I will stop here.